Great. Welcome back, everyone, to the final session of Data Modeling Zone Europe. Now, it's the last session, but definitely not the least. It's a wonderful session. We have Rafid Reaz from Scotiabank here with us, and his topic is reverse engineering, the overlooked tool in the modeling toolkit. Rafid entered the data modeling space at the age of 22. And what's amazing, too, is he became the 10th person in the world and the first Canadian to actually pass the data modeling certification. It's a very challenging data modeling exam, and you can learn more about that at the Data Modeling Institute's website. So really great, and also he has experience in both relational and analytics, and he's performed some in-depth analysis of capital markets, retail banking, insurance. He's worked on both the relational side and the NoSQL side. And just like prior sessions, please ask lots of questions. And it's my pleasure to introduce Rafid. Rafid, welcome.
Thank you, Steve. Okay. All right, thanks, Steve. So I'll get started. Steve mentioned my presentation is on focused on reverse engineering. So this is more a case study because this is something I've been working on at Scotiabank for the last 2 years or so. And reverse engineering is a very powerful tool in data modeling that's often overlooked, hence the title. So I'm going to begin by going over some of the objectives of my presentation. So the first one is data modeling as a bottleneck in agile development. Current world of big data and a lot of the emergence of NoSQL technology. Traditional data modeling is often seen as a bottleneck, and how do we actually evolve and change with the changing technology and the changing times? The importance of logical data modeling itself, even with the emerging new technologies. Reverse engineering in the context of a data model. Usually it's used as software engineering term or any sort of engineering term, but it can also be applied to other fields such as data modeling as well. And I'll briefly go over a case study, which is what I've been working on for the past 2 years at the Bank of Nova Scotia in Toronto. I'll talk about the evolution, how data modeling has evolved in the past decade or so, and focus on reverse engineering and NoSQL modeling tools, what's currently available, what could potentially be available in the near future as well. And then future automation and improvement opportunities for NoSQL data models specifically. This also relates back to the tooling and further how we can further improve those and automate a lot of the manual processes that have to happen when it comes to NoSQL data models. So there is a perception in the recent past data modeling has become a slight bottleneck in the world of agile development. With extremely tight timelines and increasing number of changes required for iterative agile development, it's hard for data modeling to sometimes keep up, and I know a lot of us have experienced some scrutiny around this. So logical modeling makes sense when one is trying to achieve an application agnostic database design, for example, which can still be achieved by a relational database technology. So it's important that we differentiate between application-specific development, where logical modeling becomes a little bit counterproductive in the current world of big data. So as far as conceptual models go, very few agile teams are actually creating them nowadays. So data modeling can no longer be an exercise just in the early stage of an application lifecycle. It must evolve and now be a part of the continuous integration loop, as shown in the slide, which adds value after each iteration itself. Okay. So relational data modeling has been commonly used in well-defined practice for a long time now. Modeling techniques, creation of conceptual models, logical models, and physical data models have been practiced by data professionals for many, many years. However, with the recent emergence of agile development, data modeling is facing some challenges to stay relevant. This has caused the emergence of NoSQL databases. So on the left here, we can see that this is a depiction of a traditional SQL database. And on the right, we have all the different types, some of the different types of NoSQL databases that are currently emerging. And a lot of them are being used by big companies such as Google and Amazon. Not just a single one of them, but a combination of many of these are being used by these companies. Okay. So I briefly want to go over what is NoSQL. I know a lot of us are familiar with it, but so NoSQL databases are non-relational databases that store data in other formats, in alternate formats. NoSQL databases emerged in the late 2000s as the cost of data storage was dramatically decreasing. So there is no longer a need to create difficult to manage and complex data models to avoid data duplication. So we could afford some level of data duplication as the cost of storage was decreasing dramatically. So developers, rather than storage, were becoming the primary cost of software development. So NoSQL databases were optimized for developer productivity itself. Okay. Briefly want to go over some of the benefits of NoSQL. So one of the primary ones, as I mentioned before, is that the NoSQL design is actually a very developer-centric design. So a lot of the development teams nowadays actually design the NoSQL data models themselves. Okay, so with or without the guidance of a data modeler, which could potentially cause some problems in the future, as I've seen. The main advantage of NoSQL, I find, is the flexibility of the schema, or sometimes you don't even have a schema to support the NoSQL database. Developers, as I mentioned earlier, typically assume the data model design responsibility. Another major benefit of using NoSQL databases is the support of large and unstructured or semi-structured data sets. Costs are dramatically reduced as storage costs have been decreased in the recent past. There are most NoSQL tooling options are open source solutions as well, which is great, and it's readily available for everyone. Horizontal scalability, so they're capable of growing in device number instead of having to reside in one large device. And then lastly, query optimization on database design for large amounts of data. So I'm specifically talking about big data in this case. Okay. So as I mentioned earlier, there are various types of NoSQL databases. Some of the primary ones are the key value database. Then there's column-oriented databases, document databases, and graph databases. Each of these are used for different functionalities within companies. And some of them, you'll see a lot of companies are using many of these in combination to perform different functions, essentially. Okay, so the first one I mentioned was document databases. So a lot of us are familiar with JSON or XML documents. So these types of documents are used to store the data itself. And we see a lot of nesting and hierarchical structures, which are really helpful relationships in documents. So you can have multiple levels of hierarchy in parent-child relationships, which can often is a little bit more difficult to express in a relational data model. And elements can be indexed for faster querying. So this is where the physical data model comes into play. You can retrieve data in a relatively short amount of time and very large data sets as well. So this is extremely popular with developers because they have the flexibility to rework their document structures as needed to suit their application. They can shape the data structures as their application requirements are changing over time. So it's not set in stone at any point, and it's really useful when it comes to agile development. Okay. The next type of NoSQL database is key value stores. So this is where every data element in the database is stored as a key value pair, consisting of an attribute, name, or it's also referred to as a key and a value. And then, like a relational database, but it only has two columns. Again, as I mentioned, one is the key and the other one's a value. This allows for very fast data retrieval as there's a small set of columns, but with emerging big data technologies and decreased cost of storing data, it's actually very quick to query key value stores. The next type of NoSQL database are column-oriented databases. So while relational database stores data in rows and reads data row by row, a column store is exactly as the name indicates. So the stores are organized by a set of columns. So when you want to run analytics on a small number of columns, you can read those columns directly without consuming memory of the unwanted data, so the remaining columns. Columns are often of the same type and benefit from more efficient compression, making reads even faster. So a lot of us have heard of formats like Avro and Parquet, which are very popular these days. A lot of these columnar storage store databases have Avro and Parquet files on the back end of it. So compression is a big key factor on using column-oriented databases. So columnar databases can quickly aggregate the value of a given column as well. So when we want to do things like sums or aggregations, it's very quick to run those queries. So from a performance standpoint, it's really helpful. And lastly, we have graph databases. So this, to me, is the most interesting type of NoSQL database. So this actually focuses on relationships between data elements itself. I would say over the actual data itself. Okay. So each element is stored as a node on the graph database. The connections between these elements are links or relationships between the nodes. Right. So this is optimized to capture and search the connections between data elements, overcoming the overhead associated with joining multiple tables in SQL. So some of the use cases include fraud detection, social networks, and knowledge graphs. I know knowledge graphs have been a big topic in the data modeling zone so far, and there's more to come regarding that. So one of the examples that actually Steve introduced me to earlier is things like LinkedIn. A lot of the social networking applications or software like LinkedIn or Facebook actually use graph databases in the back end that really focus on the relationships rather than the data itself. Okay. So these are some examples of the actual the physical databases and the software that's used with them. So we're all familiar with the relational ones, like the SQL databases such as SQL Server, Oracle, and MySQL, and Postgres, for example. Some of the common key value pairs, the key value stores are there are a few for Windows, and then like Azure Cache and the blob storage is a really big one as well. Some popular column family databases are Cassandra, and HBase is a really big one. And there are various document databases, and this has been used quite a bit in the past. I would say document out of all the NoSQL databases is the most people are the most familiar with so far. So MongoDB is a really big one, and then you also have RavenDB and CouchDB. And then one of the most popular graph databases is actually using Neo4j itself. One of the emerging ones are Stardog, which actually I was using at Scotiabank to create some knowledge graphs as well. Okay, one key a topic that I brought up earlier is that when storing data, sometimes we use it's best to use multiple data storage technologies, and each of them have to be chosen based upon the way data is being used by an individual applications or even individual components of a single application. So different kinds of data are best dealt with different data stores. That's where the term polyglot persistence comes. So if we look in this diagram, you could have a single application or some application server, and with the different components within that. And then you could have different types of databases based on individual functionalities within that application or server itself. So, for example, you could have a document database which stores user accounts, activity logs, or a product catalog. Graph database, as we mentioned earlier, for social networking data, for let's say friends, products, purchase ratings, etc., like LinkedIn. And then column databases to store activity logs. For example, Amazon uses column databases a lot of the time to retrieve data very quickly, such as, let's say, price or inventory, things like that. And then you have your RDBMS, which we're familiar with. So for things like mainly reporting. And then we have key value pairs, which are really big in, for example, shopping cart and session data, where we need to retrieve data very, very quickly. That's why when we log on to things like Amazon, we can actually retrieve product data and cart data very quickly and place our orders, and everything is very smooth because we have a combination of these databases working in the back end, and primarily key value pairs for that specific purpose. So now I want to get into some of the disadvantage of using NoSQL databases. Um, these are some of the ones that I have actually encountered when starting my role at Scotiabank, because um, their primary data store was actually using a NoSQL database called Avro, which is a document DB. So the first one is lack of data integrity. So not all NoSQL databases contemplate the atomicity of instructions and the integrity of data. It's sometimes it's actually hard to pick up a lot of the details about data integrity itself, and even do some of these checks that we do when it comes to relational databases. Sometimes it's extremely hard to query because these are more developer centric, as I mentioned earlier, and a lot of organizations actually don't create a reporting layer on top of it per se. And business users and even technical users alike have to actually go in and query the NoSQL database directly. So what I've seen is there are many compatibility issues with SQL type of instructions, right? A lot of people, technical users and business users alike, are familiar with writing SQL queries, for example. So these new databases use their own characteristics and query language a lot of the time, and they're not yet 100% compatible with the SQL used in relational databases. So some of the along with this problem comes the support issue. So some of the support for query issues in a NoSQL database becomes more complicated and less readily available from my experience. Another issue, a potential issue, is the lack of standardization. So there are many NoSQL databases, and there's still no standard like the ones that exist in relational databases for many of these as well. Okay. Additionally, one of the main problems that I've had was that the tools for data modeling are less available and not as mature for the ones that are there for relational databases. A lot of these are in their primary versions. Even things that we're familiar with, like Power Designer or Irwin, have only recently started supporting data modeling of NoSQL databases. So they usually have less useful and less mature modeling and data management tools alike. So NoSQL data models cannot be easily used as a communication tool as well. And since the beginning of my career, we've learned that one of the primary goals of data modeling is to actually create a data model that can be used as a communication tool or a wayfinding tool. So it's really hard to, for a lot of these NoSQL databases, to extract the underlying data model itself or the diagram. So for any review, you have to have either a really technical user or someone that's familiar with these NoSQL data stores to actually go in and do a business review of them. And then there's less data model review and governance opportunities as well, for the reasons I just mentioned previously. And another thing that a lot of people who are really comfortable with SQL queries are not used to is the repeating data or data elements. So because we're actually not really worried about the quantity or the amount of data that we're storing, more how to store it, because that is what NoSQL optimizes. A lot of the time, and actually most of the NoSQL data stores, you'll see a lot of repeating data elements. Users have to, if there is not a reporting layer that's created on top of these, users actually have to go and dedupe a lot of these when they're writing their queries or their code for this. Okay. So similarly, there are various advantages of actually using a relational model that go hand in hand with some of the disadvantages that we've seen for NoSQL data models. So one of the primary things are they provide structural independence. So there's separation, as we know, the logical data model, which focuses on the business needs and requirements, and the physical data model, which focuses on technology. With NoSQL, it's most of the time all you have is a physical data model, and there's an underlying logical. And basically, in all cases, there's rarely a conceptual data model that's created. Advantages, it can be used as a communication tool to improve conceptual simplicity and increase understandability quite a bit. So every single user or various different groups within an organization can use the same data model, whether it's an enterprise-wide data model or not, as a communication tool to describe a certain functionality of the business or a business as a whole. Ad hoc querying capability using query language that majority of users are more comfortable with, like SQL, is there. So this is one of the complications that we have with NoSQL is that a lot of users are not comfortable writing the NoSQL queries because it might be a little bit new, and then a lot of the times it's not 100% compatible with the SQL that we're used to. Also, there's well-established data modeling, data governance, and overall data management practices, which have been tried and tested for years that are being implemented for relational data models. Additionally, as we mentioned, data integrity is a big problem for NoSQL databases. But as we know, that's one of the biggest strengths of a relational model, that data integrity constraints are actually model. Okay. So just like a relational model, one of the important parts of a relational model is the logical data model itself. And a lot of the time, a logical data model, as I mentioned earlier, is lacking in a NoSQL database. A logical data model is a graphical representation of the information requirements of a business area, as I mentioned before. So it must be independent of technology, since technology changes so rapidly. So we need the stability and structural independence of the logical model itself. So sometimes we describe it as the difference between what the business requirements are and how they're accomplished. So this actually outlines the difference between a logical and a physical data model. It serves as a very powerful communication tool for users to better understand the data and the business which the data is describing, or a functionality within that business. Additionally, one logical data model can give rise to many, many physical data models. Again, this goes back to the structural independence that I was talking about earlier, which are technology and application specific. The physical implementations are specific to the technology and individual applications, but the logical data model can be taken out of that context. So that's just a bit of background to lead up to the concept of reverse engineering when it comes to a data model. So usually what we're used to in IT is the term reverse engineering is usually in the case of software development solely. So software reverse engineer, SRE as we know it, is the practice of analyzing a system, either the whole system or part of the system, to extract design and implementation information that have been lost. A typical reverse engineering scenario would involve the software module that has been worked on for years and carries several rules of a business in its lines of code. Unfortunately, the source code of the application might have been lost over the years. So what remains is the native or binary code. So we can apply reverse engineering to actually to extract these rules of the business from the code itself. So what is reverse engineering in the context of data modeling? So reverse engineering is a process or function to create a logical and physical data model by extracting information from an existing data source. So some of the times, most of the times, this is actually a physical data store. It could be schema-less, and there's no real documentation on even the physical data model or the logical data model. So you may either create a physical data model from this when you reverse engineer the data itself, or a logical model, or both. In very few cases, we actually go all the way back to the conceptual level when it comes to NoSQL. So what are some of the reasons for reverse engineering a data model? So a database may not be present, but there database may be present, but there may be no data models, whether it be physical, logical, or conceptual. Uh, Additionally, a data model may be present, but it may not be in sync with the current database. When integrating data from different sources into one database to create a data warehouse, for example, some sources may not have the source data models, which represent the source data as is. So we use reverse engineering to create to extract the source data model from the source data and any documentation that is available. Logical data models can be given to any business community. So this includes people like SMEs or business analysts, and physical data models to the development community, people like developers or DBAs alike. There's often there's a schema associated with the data structures itself, but there is no logical data model. If we want to create something like an alternate physical representation of the data, the creation of a logical data model is required first to better traverse from one physical representation to another. So it makes it much easier to actually go back and create a logical data model and map multiple physical data models from that. From a mapping perspective, from a documentation perspective, and from a process perspective, it saves a lot of time in the long run. So there are a few known uses of reverse engineering a data model that are currently being used. So sources from which data models can be reverse engineered include Oracle, MS SQL, PostgreSQL, DB2, UDB, MySQL, MS Access, Sybase, XML files, or SQL files. There's quite a few of these. The reverse engineering wizard for each of these base modeling softwares may be different, but various known tools support this functionality to generate data models from these sources. But as you can see, majority of these ones listed are not NoSQL models, so it's more for relational models. So there are a lot of problems which arise with reverse engineering a NoSQL database into a relational data model. One of the ones I mentioned earlier is the lack of data modeling tools which support this functionality. There are a few tools which are available, but they're either in very early stages and I've found to be a bit buggy in nature. So there is a lot of manual intervention that needs to happen and a lot of grunt work that happens by data modeling professionals to actually reverse engineer. So there's lots of automation opportunities in the future for these things. the data modeling tools that do reverse engineer NoSQL databases into a tabular view, as I mentioned, their earlier versions have lots of bugs. Apply very basic knowledge to create these tables. For example, the output is often not a useful data model, but it serves as a basis actually, or a starting point to start the reverse engineering process and create a logical or physical data model. However, if the functionality works, it could be used to save a lot of time in the process itself. Maybe the entire thing won't be automated, but a lot of the grunt work and the legwork would be saved in the initial phases of reverse engineering. It also requires additional funding and time to build out the logical data model. So a lot of the times when you're actually a lot of data modelers have experienced, it's more of a sales job a lot of the time. So it can be difficult to make an argument to get funding and resources to do this exercise, because there's no concrete immediate use, or it's hard to convince a lot of users or SEs or higher ups that this is useful in the short term, whereas there's definitely a lot of long-term benefits to creating a logical data model. There's also a lot of additional documents that need to be maintained and artifacts, and these need to be updated every time the schema is updated and there are new requirements. So again, it goes back to being a slight bottleneck in agile development if this isn't done in the right way, and it can't keep up with the incoming requirements, which are really fast when it comes to NoSQL a lot of the time. Additionally, there can be potential new governance structure that is required. Since the logical data model represents the business, it's important to have business reviewers who are experts in the different subject areas reviewing the data model, and any changes made to the data model, it's to hand in hand with the maintenance of additional documentation. This could add to the time required to actually turn on any changes or any data models, and in turn update the actual schema itself. So in the development community, a lot of the times it's seen as a bottleneck. Okay, that leads me up to my case study, which is actually reverse engineering an Avro schema, which is a document store, into a relational model. So during the last role at Scotiabank, I had the opportunity to reverse engineering NoSQL schema into a semi-normalized relational data model. What did the existing data model actually look like? The format of the data was Avro, as I mentioned earlier. The format of the data model is actually an Avro schema, which is very similar to an XML schema or a JSON schema, and it's hierarchical in nature. And there are modeling tools that are similar to XML Spy that can be used for Avro data modeling. Where I worked in Scotia, within that group, which is capital markets, it was a federated model. So what that means is they require and it was implemented by a technical team, a development team. So data producers were the owners of the model and the subject matter experts in their respective domains. All the data modelers could actually do was provide some guidance and some feedback to schema changes. But at the end, the producers had the final say. So standardizing, as you can guess, was quite a problem, because you have different applications giving you requirements, and they want the data model as is within their application. So what was the problem statement that I was approached with when I was initially given this role? The primary one is difficult to understand the model by reading the Avro schema itself, and it's hard to query, especially for less technical users. So there's a lack of diagram representation for ease of understanding. There was no logical data model to understand and communicate the business processes. Data delivery and management were driven by a technical solution. Avro format was used for data storage, transfer, and reporting. There's a complete lack of data governance, so there's no established governance structure for a data model review, expansion, and maintenance. And the data dictionary often came from the producers with very little review by a data modeler. These producers are often an individual application with a purely technical team running it. There's also inconsistent application of data modeling standards when the schema was being created for things like entities, attributes, and relationships. There's a constant difficulty to identify a data owner for the overall data model or subject areas within the data model. And there is, as I mentioned earlier, duplication of data elements throughout the entire schema itself. So this caused a lot of confusion when actually reading the schema and querying the data. And there's a lack of harmonization of requirements. So what that means is if there were multiple producers that were giving the same requirements, the same requirements might have been modeled in different ways within the same schema. So there might have been a duplication of representation of requirements. Whereas what we're used to in logical data modeling is when we get a requirement, we actually compare it with all existing requirements and existing data elements within the model. But this schema that I was dealing with was so large, with tens of thousands of attributes within it, the Avro schema, that a lot of the times there was no way that the requirements could be harmonized as fast as the requirements were coming in. There were over about 150 data producers all sending requirements at the same time. So there's also difficulty applying a standard data integrity and data quality checks by people like the DQ teams or the QE teams, and even the data modeling groups because of the nature of the schema itself. And it was being run by a purely technical team. Okay, so I'll briefly go over the actual reverse engineering process. Initially, a certain version of the schema was locked down. Any requirements that are implemented during the reverse engineering process can be backfilled at a later point. The initial point is try to get as much of the model created as possible and adhere to that one version to avoid a moving target. So this is just an example of what a hierarchical message looks like. So you could have things like a parent-child relationship, as you can see here. Within order, you have attributes like order ID, and each of them has a data type itself. And then you could also have salesperson, and there's a salesperson ID and a first name and a last name and a phone number. These are all hierarchical messages in nature. So now the whole goal was to create a diagram representation. So there are some existing data modeling tools which have recently added functionality to do this, like Irwin, but as I mentioned earlier, most of them are early version. So this part required a lot of manual work unless it was done programmatically, which is possible. And I chose to do it through Python, a lot of it, and it saved me a lot of time. So a lot of the entities, attributes, and relationships, cardinalities, and data types, nullability needed to be defined accurately to represent the schema as is. And things like surrogate keys and foreign keys, which are missing in the Avro schema, needed to be added to represent the hierarchies or the hierarchical structures within the schema. Okay, so this is an example of how that the Avro message that we saw earlier can be reverse engineered into a relational data model. This is just a part of it. So you have order, and then you have salesperson, and then something like customer. Okay. These types of data models we're very used to seeing, and it's a really useful communication tool for business users and for non-technical or people who aren't used to NoSQL querying itself. Okay, so how is the logical model created from this physical diagram, representation? So the Avro schema itself was used as requirements. I used the various logical data modeling techniques, like normalization was the biggest one, and then application of data modeling standards for entities, attributes, and relationships, and the data dictionary was updated where possible and allowed. And then I referenced a lot of the financial industry standards like FPML. Okay, so when we further normalize that those set of tables that we've seen before, we can see that uh, this can be the salesperson, the customer we had, can actually be modeled as a party table. So this is really useful, things like this, when it comes to a logical data model, because it's much easier to understand and avoids a lot of the data duplication. In the physical layer, of course, this could be again broken out depending on the technology that's being used. So some of the steps to increase usage and understanding of the data model were I had to maintain a mapping document between the logical and physical data model, which is the Avro schema. The logical data model was broken down into smaller subject areas so that the information is easier to digest. For me, it was product class and trade life, what phase of the trade life cycle it was in. And then the subject areas of the logical model were reviewed with appropriate business users, and we were also at the same time assigning data owners to these subject areas as well. Then it came to a point where we wanted to get into the technology part of it and make it create a reporting layer which was easy to query through through SQL like language. So it's time to materialize the semi-normalized relational model to create views that are easier to consume. So we started with the logical model. I applied physical data modeling techniques based on the technical requirements like denormalization to make it more easily consumable and faster to query, and ended up choosing the most appropriate database for reporting, and materialize one subject area at a time for users to query and test them and make any changes to the data model as a physical data model as required. So this is something like that the physical ended up looking like. So the schema turned into the three tables in the logical layer, which was later normalized into two tables, and then the physical was actually put into a single table in Hive, which had a lot of columns, and storage is not usually an issue. Okay, so now we have created a separation between the business requirements and the technical solution. So it's really easy to create multiple data models for different purposes, physical data models from the same logical data model. There's also many use cases that are being used where there's a combination of structured and semi-structured data. So there's a combination of, for example, relational JSON um, data elements. So for example, if you look on the screen, the structured data described by the schema includes name, latitude, and longitude, and then the semi-structured data actually has these key values that are mentioned here. So this is kind of a hybrid, a relational and NoSQL data model. In terms of data modeling software, there are lots of existing and new data modeling tools that are starting to support NoSQL data modeling. There's still a lack of documentation and support and coverage for these tools. Most of them that support these are primarily focused on the document databases, and not a lot of them for graph or some of the other types of NoSQL data modeling. But there is hope for further creation of automation and support for NoSQL data modeling tools in the future. So what could be some of the future automation improvement opportunities for NoSQL data models? One of the biggest things was better data modeling tools, native visual representations of NoSQL databases that are created when the schema is actually created itself, new tools or additional functionality in existing tools to support reverse engineering process, which can be quite tedious at the moment and a little bit hard to sell. Further improvement in data visualization tools for NoSQL databases, and improve support and documentation for these database tools itself. Another big thing is automation, automated data model extraction from application source code, which can be extremely useful not only for NoSQL but SQL models alike. Um, Automated code model data consistency validation and metrics. So this is something like a reconciliation exercise that is run in data models a lot of the time, and better control for application data model change management. We also can focus on proactive tracking and reconciliation between application code, data models, and actual data in NoSQL databases. So this leads to the evolution of data modeling itself. As I mentioned earlier, it needs to be integrated as a part of the agile development process that is being widely used nowadays. Um, so for conceptual models, diagramming techniques such as entity relationship diagrams can continue to be used as to model NoSQL applications. We need to be able to bridge the understandability and usability gaps during the transition from SQL to NoSQL databases. So this includes things like additional documentation for physical and logical data model representations, a data dictionary, mapping documents. We can help this data modelers now can help design user interfaces or views that make it easier for the users to view and query the data. And data and metadata management is a big space where data modelers can contribute, where we can establish and maintain proper data modeling standards and data management practices in general. Another big thing that's up and coming is semantic and ontology modeling for better understanding of the metadata, data, and the relationships between two. This is somewhere, for example, that graph databases come into play. So with emerging NoSQL technologies and big data itself, data modeling also has to evolve and keep up with the ever-changing technology. So these are some of the ways that we can do that. I'm currently about 90% done actually creating the logical data model for my role at Scotia. And it's been a long process so far, so there's definitely lots of automation opportunities that can be used. So, but it's definitely doable for anyone who's worked with NoSQL databases, and there are many benefits. Some of which I mentioned earlier, to having a relational representation or a tabular view, and logical representation or a logical data model, and all the documentation that comes with it. Okay. So that concludes my presentation. Thanks for listening. I guess we can open it up for questions if it's not too late. Steve?
Yeah, perfect. Thank you, Rafid. Yeah, we have a bunch of questions. I'm going to just scroll up here and start with the first one, which is,
Yeah.
how do you classify the Parquet files? Like, where are they classified in the scheme of things?
Yeah, so a lot of the times actually Parquet files are not used as a they're not actually there's no schema to actually represent the Parquet files. This is primarily used just for compression. So what happens, for example, is let's say you get like something like an XML file or a JSON file. Parquet is actually used to compress that data, so the actual storage requirements are reduced. But users often don't actually see the Parquet compressed file when they're querying. There's often a reporting layer on top of that, like a database that sits on top of the Parquet file and reads the Parquet file directly. So a lot of the big data technologies like Hive use Parquet in the back end for compression purposes.
Got it. Thank you. And question from Marco. In looking at all the different modeling tools out there, have you had a chance to check out Hacklead?
Yeah, Hacklead is something we've been looking at more recently. But what I was actually using was, it takes you, like a lot of these tools, the problem is it takes you part of the way there. So I found that when you want to do an end-to-end like reverse engineering solution where you actually get a usable data model out of it, there's a lot of manual intervention, or like if you want to do it programmatically, that's possible. But like a lot of these tools, it doesn't really at this point provide a solution for all the use cases.
Got it. Got it.
Yeah.
Thank you. And question from Yuha. So, how do you attach semantic meaning on a reverse engineered model? An auto-generated schema diagram from, for example, SAP doesn't really mean anything to normal human beings. And even if you are able to translate the technical names to business names, it's still a description of how one system stores information and not how the business works in reality. Oh, that's very interesting. Yeah.
Right, right. Okay, yeah. So what we've done is actually when I've actually run into this when a lot of the data elements that are actually in the schema itself are very technical and don't really have a lot of business meaning. So there's quite a bit of like compromising that goes on in these cases. So as I mentioned before, like you basically all you can really do is push for majority of the data model to be created in the reverse engineering process, and that can have some semantic meaning to it. And you have like a metadata layer that's created on top of it, but there will always be some portion that's application specific, which you don't necessarily need to represent in the logical data model, but could potentially be represented in the physical layer itself. But essentially, what we did was we created from the data itself. We created a knowledge graph using a tool called Stardog, and that is actually what's used as the underlying semantic data model or the ontology representation, right? So that's completely separated from the actual data model itself, right? They're interlinked, but it's not one and the same thing.
Got it. Got it. Thank
Yeah.
you. Yeah. What's the name of that graph tool again? I'm sorry.
Stardog.
Stardog. Okay.
Yeah.
I'm gonna check that out. Thank you.
Yeah.
Yep. And then a question from Marco too. So, what was the driver behind reverse engineering to begin with? Was it that the original system was not modeled initially? What was the
Yeah.
driver there?
Yeah. So I've actually experienced this in previous, like two of my previous roles, where I think it was a lot of these. What happens with the big data stuff is people want to jump into the technology and not the data modeling aspect of it. So what happened in my case was that Avro was chosen as the data reporting mechanism about 5 years ago, and then it's been widely used. But now that more and more users are actually getting interested in this and using the data, the problem is one, it's really hard to understand the schema, right? When you look at an Avro schema or even a JSON file with tens of thousands of rows, it's quite difficult and extremely technical to actually extract information out of the schema, right? So you need to either have a layer which like dedupes and harmonizes the requirements and things like that programmatically, or a lot of the times it's not possible. But then the other driver was one was understandability, as I just mentioned, and the other driver was actually queryability of like existing users that are used to SQL queries. Found it really difficult to actually query a hierarchical message, right? Because it's all in hierarchies. You don't have the inherent foreign key surrogate key relationships, for example, right? So you actually have to look at things like indentation within the schema to
Right.
pick up these relationships. Yeah.
Wow. All right. Yeah, that is not easy to do.
No, not at all.
Great. Great. Thank you, Rafi.
Yeah.
We're actually right at the end of our session time. Great questions. Great presentation. Thank you
Thank
very
you.
much, Rafi.
Thank you.
Good luck with everything, too.
Yeah. Thank you. Take care.